good morning and welcome to the last Saturday Physics for Everyone for 2016. Today we are very happy to have Professor Verena Martinez Outschoorn. Verena was an undergrad at Harvard. She did her PhD at Harvard before she was the Letterman Fellow at Fermi National Accelerator Laboratory. She's now faculty here at the University of Illinois. Today she's going to take us on a very exciting visit to the Large Hadron Collider.
Okay, thank you very much. Thank you, all of you, for coming. It's a pleasure to be here. And so today I'm going to take you on a little virtual tour of the Large Hadron Collider, and in particular, one of the experiments there that you can see in this picture. So first, I'm going to give you an overview of the LHC and the detectors. And then we're actually going to connect with some scientists who are currently, right now, they're working on our experiment out in Switzerland. And they are right now in our detector control room. So this is the room where the scientists operate the experiments from. Okay, so we're going to hear live from them. So one thing that I want to ask everybody here is if you can please think of, all the questions that you ever wanted to ask, an LHC physicist, okay? And when we connect to CERN, then if you could please come down here, and we have a microphone so that we can talk to them. And please, ask them whatever you would like, okay? So, okay. So, in particle physics, what we're interested in is to understand what are things made of. And as you know, so here are some examples. We know that things are made of molecules. So this is an example of a molecule that causes the blue pigment in the flowers and the grapes that I just showed you. Okay, so we learned that stuff is made out of molecules, and molecules typically have a size of around 10 to the minus 9 meters. But we know that molecules are actually made up of smaller components, right? So molecules are actually made up of atoms, and atoms are an order of magnitude smaller, something like 10 to the minus 10 meters. But we also know that actually atoms are composed of other constituents, right? So they're made up of a nucleus and of electrons. And if we strip away these electrons, we can see the nucleus, which is of an even smaller size, 10 to the minus 14 meters. And we also know that, in fact, if we zoom in and look at it closely, the nucleus is itself a composite object, okay? It's made up of protons and neutrons. However, if we were to zoom in even more, right, we know that protons and neutrons are actually made up of quarks. Okay, so they themselves, and they are already really small, 10 to the minus 15 meters, okay? They themselves are made up of smaller particles that are the quarks. And in fact, the quarks, as far as we know, they have no dimensions, okay? We don't know anything smaller than the quarks, okay? They are like points, if you will. Okay? And so the idea behind particle physics is we can understand things made up of larger objects, but actually, for example, understanding that molecules are made up of smaller parts like atoms helps us understand why molecules are the way that they are. So by going to smaller and smaller scales, we can try to gain some insight into how the bigger building blocks are formed and what is the bigger picture. So the last thing I wanted to say is that the physics that we use to describe these different scales is very different. And what we are really, after in the experiments that I'm going to talk about are really these very, very fundamental building blocks that are these point-like particles. Okay, so what are these fundamental particles? So the most well-known are the up and down quark. They make the protons and neutrons. And we also have the electrons and the electron neutrino, and these compose most of the atoms that we know. However, there was a really interesting discovery in 1937, and this was the muon. So what happened then is that people started to look at particles that were coming from showers that were produced in the atmosphere. So particles that were arriving to Earth, and these are cosmic rays, and some of these particles are muons, and the muon is also a fundamental particle. It's just like the electron, but it is 200 times heavier. So this was a very surprising thing. So now suddenly we have this kind of picture. And what happened is, over the years, we filled out this little table. So what we found is that, in fact, we don't just have up and down quarks and electrons and electron neutrinos, but we have 3 generations of particles. And these particles are divided, so we have the quarks and the leptons, and they have particular properties, so they have a particular value of the electric charge, and all these particles have an intrinsic angular momentum, or spin, 1/2. And these are the particles that really are the fundamental building blocks of matter. So one of the main things that distinguishes these different generations is that they have increasing mass. And what's very what is really an experimental observation, but we find very intriguing, is if you look at this plot, I've shown you the masses of some of these particles. Now keep in mind that each one of these thin lines, this is a log scale plot, so that's a factor of 10, okay? So these particles have a really large range of masses, that span several orders of magnitude. The electrons are really small, and then up here we have the top quark that is very heavy. And this is one of the questions that we have in our field, is why do we have this wide range of particles, and why do the masses have these particular values? And we don't know why that is. I should mention that the top quark is very special. The top quark is actually from Illinois. He or she was discovered in 1995 at Fermilab by the CDF and D0 experiments. And you can imagine the top quark is so strange, okay? Its mass is huge. It has this single fundamental point-like particle has the same mass as a whole tungsten atom. Okay, so a tungsten atom it has 74 electrons and 74 protons and 108 neutrons. So this is in a single particle. So it is a very, very intriguing thing. Very heavy. So far I've told you about the matter particles. We also have other particles that are called the gauge bosons. These particles, the last of these were discovered already in the 80s. They also have, some of them are charged, some are neutral, and they all have spin 1. So the intrinsic angular momentum is 1. And these particles are known as the force carriers. So they are responsible for phenomena from electricity and magnetism to weak decays that cause radioactive decay, and the strong interaction that is what binds together the inside of nuclei. And the last piece is this new particle that we discovered in 2012 that I'm going to talk more about. And this particle was discovered after a hunt that took 40 years. It took scientists 40 years to discover the Higgs boson since it was predicted. And what's very interesting about the Higgs is that it's the only particle that has no spin. It's the only fundamental particle that is spinless. And in fact, it is very important piece of this picture because it is necessary to give masses to all the particles in the standard in this diagram. And as I mentioned, so mass is a really important property. So this is, in summary, our knowledge this is like our periodic table of fundamental particles, and this is called the Standard Model. And all of these particles we have studied very precisely in our experiments. And there have been many experiments at CERN, the European Laboratory for Particle Physics, at SLAC, this is outside of Stanford in California, at Fermilab outside of Chicago, and other labs around the world. And so we understand a lot about how these particles behave and what are their properties thanks to these experiments. Okay, so I have talked about this question of what is the world made of? And this is, of course, one of the basic questions in particle physics. However, we have a number of other questions that we're interested in. So we're interested in what is the universe made of? Why do particles have mass? Remember this question that I brought up before, and why do they have those values of mass? Another question that, for particle physics is really important is what is dark matter? Dark matter, which you heard a lot about in the last lecture, right? Is excuse me, could be a particle. And, but we don't know what kind of particle it is, and it would be great if we could produce it at the lab. We also are interested in knowing if there are other particles or other types of interactions. And then there are other questions like, for example, why in our universe do we see mainly matter and not antimatter? So antimatter is another copy of the particles that I showed you, but basically with opposite charge. And understanding this small picture can actually also help us understand the very big picture. So for example, why the universe evolved to look the way that it looks like today is a question that we can also help answer in particle physics. So the way that we produce particles in the lab is thanks to a very famous phenomena that it comes from Einstein. So what we do is we produce very high energy collisions, and we can convert the energy of these collisions into new heavy massive particles. So this is the famous formula from Einstein. If you look at the full formula, so this formula is valid for the case when particles are at rest, but when the particles are moving at high speeds, which is going to be a case that we're interested in, we actually, the mass is going to be related to the energy of the particles and their momentum. And so we're going to use this to produce new particles and study them in the lab. So here is a diagram showing you where the Large Hadron Collider is located. So this is the machine that produces the highest energy collisions in the world. Okay, so over here is Geneva, Switzerland, and here is the lake. And it's a very large ring. It's about 17 miles in circumference. Okay? And for scale, you can see this is the landing strip of the airport in Geneva. And actually, I thought just for fun, I would just to show you how large it is. Okay, if we take, if we were to transfer the LHC ring around Loomis Lab, okay, it would basically cover most of the Champaign-Urbana area. Okay, so it's really a very large machine. So here is a picture of what the LHC looks like inside this giant circle. So it is a tunnel, there's a tunnel, and inside of it we have these very high-tech, over 1,000 of these high-tech magnets. And these are actually superconducting magnets that are maintained at very low temperatures. And these magnets produce very high fields, 8.3 Tesla. And the reason why we need these very high fields is because through these pipes over here, we have protons, okay, that are rotating around. And you can see that it's so big that you can barely see the curve, right? It almost looks like a straight tunnel. And so in order to be able to maintain particles of a certain momenta in this circular trajectory, we need to have very large magnetic fields and also a very large radius for our circumference. And so this is what drives this requirement. But these superconductors, it's really a challenge because they only operate at very low temperatures. And actually, you could say that the conditions, we're sort of recreating the conditions from outer space inside of our accelerator. So the air pressure inside the vacuum tubes is very low. It's like 10 to the minus 13 atmospheres. So it's like lower than in the moon. And also, we cool the magnets down to minus 271 degrees Celsius. So that's like very close to absolute zero. And that's also colder than in outer space. And I should say that this system over here, so this is a view of people inside the tunnel to give you kind of a sense of scale. Oops, sorry. To give you a sense of scale, so these are, different kinds of magnets that some of them bend the particles and keep them into their trajectory. Others focus the particles so that we can produce these collisions. So you can see this is quite an engineering feat, and it's actually the largest cryogenic, cold system in the world is this machine. So it's really, one of the most complex things that humans have ever built, actually. Okay, so going back to our picture, so in the LHC ring underground, we have counter-rotating beams of protons, and at certain points, so we give these beams as much energy as we possibly can, and then what we do is we smash them together as hard as we can. So we try to make the most energetic explosions that are possible, humanly possible, okay? And then what we do is we hope that in these collisions, the energy of these colliding protons can become new particles, new heavy particles, new things that we could, in principle, see. So we build our detectors around these collision points. And what happens is these particles, they decay almost immediately. Question?
Would there be any advantage to studying proton and antiproton collision instead of just proton-proton?
So the question, for those of you who couldn't hear, was if there is an advantage to studying proton-antiproton collisions. So we have in the past, so for example, the Tevatron, which was the accelerator at Fermilab, did collide protons and antiprotons. And it turns out that it is very interesting to collide proton and antiprotons to see certain processes. But when you go to very, very high energies, in the protons, remember that I told you that there are these quarks inside, and the quarks interact. Well, what happens is we also in the proton have a lot of gluons. These gluons are the particles of the strong force that hold these particles together. And gluons also interact. And in fact, they are the particles that interact the most at high energies. And so it turns out that at very high energies, there's not such a big difference between colliding protons and antiprotons versus protons, because they all have lots of gluons. We're basically, at these very high energies, we are basically colliding like balls of gluons, if you will. So, and also it's easier to work with protons, because basically our protons, they come from like a bottle of hydrogen, right? Whereas antiprotons, you have to work harder to produce in the lab. They're not as common, let's say. Did that answer your question? Okay. Okay, so these new particles, they decay almost instantly. And so what we do is we actually study in our detector the decay particles. And if we go back to that formula from Einstein, we can actually tell what was the mass of that original, the parent particle, by looking at the properties of the decay particles. Now, something that I think is very interesting about this Einstein theory of special relativity is that the mass of the sum of these two particles, okay, so the parent particle is not just the sum of the two masses, right? So for example, if I go to the store and I buy a pound of bananas and a pound of oranges, I would measure 2 pounds. But this is not how it works, when things are moving really fast. In fact, the mass, it also is going to depend on the energy and the momentum, like how fast those particles are moving. Okay, so we have this more complicated formula, and actually if the decay, it's really crazy because even you can have particles in the decay that are massless, for example, like a photon. However, they can sum up to something that has mass. Okay, and in this case where the decay particles are basically massless, this is the formula that we get. And what we find is that if we want to learn about the parent particle, what we have to do very precisely is measure the energy of the decay particles and the direction that they were going in, so the angles between them. Okay? So if we can measure these things really well, then we can determine what was the mass of the particle that produced these decay products. Okay, so in order to do that, we have to build very big detectors around the points where we collide the protons together, right? So we make these explosions and lots of particles come out, and we want to measure their decay products. So we have on these two sides of the ring, so CMS is out over here, so this is in the French countryside. And then the ATLAS experiment is over here. So this is closer to downtown Geneva, is kind of where my pointer is right now. And this over here, this triangle, is the CERN campus. So this is the European Laboratory for Particle Physics. So these detectors are quite complex. So here you can see this is a very schematic diagram of CMS and ATLAS. And you can see these for scale. These are people, okay? So they're very large. And here what we've done is they have a kind of a cylindrical shape. And what we do is we make a cutout so that you can see, because it's made up of different layers of different kinds of detectors. So I'm going to tell you a bit more about them, but in the inside we have tracking detectors, then we have detectors that are called calorimeters. These are all inside of magnets that provide a magnetic field, and then out here we have muon detectors. And as I was saying, we have to make these detectors really long and really big. And the reason is, so the reason for the large size is because we have to measure, we basically have to contain the energy of these massive explosions, right? So you need to build really big devices to be able to absorb all that energy. We also need, it turns out that in this schematic, you can't see it, but we have lots of little detector elements, okay? There's more than 100 million individual channels that we read out. And the reason for this is because in every one of these explosions, we actually produce over 1,000 particles. So in order for us to measure these particles, we need to have lots of separate elements. And the other thing that we need to do, and we need to be able to measure them very precisely. Remember that I was telling you to measure these directions of these decay particles. It's really important. And finally, we also need to have very fast detectors, because these collisions, they happen all the time. They are basically happening 40 million times every second. Okay, so in order for us to process that amount of collisions, right, we have to be really fast. Otherwise, we're going to miss the next, and what if the next event was the one that had the new physics in it, right? We wouldn't want to miss that, right? So we have to be, it has to be really fast. And these guys, I mean, so you see they're really big, but they weigh about 7,000 tons each. So that's like putting the Eiffel Tower inside of a cavern, basically. Another number that I really like is it's about 3,000 kilometers of cables that we need to be able to, read out this huge amount of data. So it's just of an enormous scale. Okay, so I wanted to show you a little video about the basic idea behind particle detection. So we have these different layers. On the outside, we have muon detectors that are special detectors to measure muons. I'll show you some pictures in a minute. And then over here, we have the calorimeters. So the calorimeters, they're going to absorb the energies of the particles. So these particles are going to basically smash into them and shower. Okay, so that's what is represented by these diagrams. And depending on the type of particle, they shower in different ways. And then if we zoom further in, we have what are called the tracking detectors. And these measure the trajectories of charged particles that bend in a magnetic field, while neutral particles are invisible to the tracking detectors. So let me tell you a little bit more about how these detectors work. So to measure the direction, we use dedicated detectors that are the tracking detectors. And the basic idea is that we have charged particles that traverse our detector elements, and they will knock out electrons in the material of our detector elements. And then these electrons, we can make them, move in the presence of an electric field, and then we can record them in electronics. So that's how we measure, we detect that one of these particles went through our detector. And so the idea is that we make several layers of these. So when a particle goes through, it leaves certain signals, right, in a particular pattern. And then what we do is kind of like connecting the dots, right? So we reconstruct the trajectory of this particle, right? We infer where the true particle went because we can see the signature of the particle as it traversed the different layers, okay? And we have different types. They are gaseous detectors, so this is filled with gas, or it can be filled with silicon. And here are some pictures, so you can see what the trackers look like in ATLAS. So this is an example of one set of these layers. So it's like made up of little modules. Each have a bunch of different channels so that we can identify what specific points these 1,000 particles that get produced went through. Here you can see an example of, this is a different kind, this is a gaseous detector that is built into some tubes that are filled with gas. And over here you can see somebody during the construction of ATLAS putting together these different cylinders, one inside of the other. And over here you can see an example of what, so one of these collisions, what it looks like. So as you can see, we've kind of color-coded each of the different particles, but you can see that each particle, as it goes through the different elements, leaves these dots, and it becomes quite a fun, puzzle of connecting many, many dots together and figuring out, how everything works out. So each one of these corresponds to a different particle. Okay, then the other thing that we need to measure, if you remember, is the energy. So to measure the energy, we use calorimeters. Calorimeters are referred to as destructive detectors because basically the point of the calorimeter is to stop the particle. So the particles just smash into the material and give it all its energy, and that's how we measure the energy of the particle. Okay, so in particular, we can measure really well electrons and photons, and then the quarks and gluons, they produce at these very high energies jets of particles, or sprays of particles that we can also measure in our detector. And so these detectors are made up of two different kinds of materials typically. So one is like lead, a very dense material, right? That is what is going to literally stop the particles, right? So that's what the particles are going to hit. And then we also have interspersed in between a material that we can use to read out, to do the energy measurements. Here you can see, so in ATLAS, our calorimeter has a very nice kind of a zigzag shape. And here in this diagram, you can see this would be the pattern of energy deposition that an electron or a photon would leave in our detector. So it has a very particular shape that we measure. So here you can see some nice pictures from the construction of ATLAS. So this is the calorimeter that I mentioned that has this very nice zigzag pattern. Here you can see there's a separate calorimeter. So this one measures electrons and photons. This one measures hadronic particles, so particles made up of quarks. It's made up of these material called scintillators. Actually, I should mention that here at U of I, we built a lot of these detectors that are now, they were transported. So these are multi-ton detectors that were then shipped off to CERN and are now operating over there. And this is what it looks like once everything is all installed and sealed. And you can see that we're measuring the light signals that correspond to the energy depositions of these particles in the detector. And over here you can see, so this is a display, so you can imagine the two collisions coming in. They produce this spray of particles that we measure in the tracker, and then these kind of towers correspond to the energy depositions that are measured when the resulting particles interact in the calorimeters and deposit. So the size of these towers basically tells us how much energy was deposited. Okay, and last but not least, this is a topic that's dear to my heart because I spend my time working on these detectors. So muons. So muons are, as I mentioned before, they are like the heavier cousin or sibling of the electron. And muons are very special because they actually make it through the calorimeter. Remember how the calorimeter is designed to stop all particles? Well, it turns out that muons are special and they can just saunter through, okay? And so we built another set of big detectors way out here to measure the trajectories of these particles. So it turns out that this is very challenging to do because we have to cover very large areas. So if you remember the scale of this can easily be 25 meters. And the requirements that we have to be able to, measure things like the Higgs boson, we have to be able to measure. So here's like a zoom in to some of these detectors, and they produce these hits that look like little circles. So we need to measure each one of these points with a precision of 100 microns over 25 meters. So it really requires, a lot of care when building and assembling these huge detectors. It's really not such a simple problem. So here I have some pictures so these are pictures from when I was a graduate student and we were building the Muon system in ATLAS. And you can see, so here are some very large wheels. We're going to see a video about this in a minute, but these are some very large wheels of muon detectors. So here, just to give you a sense of scale, right, this is a staircase, and a person would be, something this size, okay? So these are enormous detectors. Here you can see when we were installing some of the chambers around, so these are the magnets in this famous picture that I showed you at the very beginning of the talk. These are the magnets for the muon system, and we install chambers in between. And this is a funny picture. So this is another wheel. It's called the small wheel because it's smaller than these guys that are the big wheels. And this guy, we built this guy whole at CERN, and then we had to transport it into, so this is the building that is on top of the ATLAS detector, and then the ATLAS detector is underground, so we had to lower this. And I had never seen anything like this because this thing weighs 100 tons, and we had to transport it in a truck that had 128 wheels, which, I didn't even know a truck could have a truck with 128 wheels. And then actually, when we arrived, we discovered that it didn't fit through the door. So we had to cut this out. But in the end, it made it nicely inside. So, and it works very nicely. So, yeah, and here you can see a picture that was when we were next to, this is just the bottom of another one of these big wheels. So you can see how big it is. This was the last day in July 2008. That was like when we finished the construction, finally, after several years working on it. Okay, so here I'm going to show you a video of sort of how it all fits together. So we're zooming in to the center of Europe, okay? So here's the LHC, where the particles are going around. This is CERN, okay? This is this building that we just saw a picture of. So this is the building that's on the surface of ATLAS, okay? And then if we can look underground, we have the giant cavity. So this is what's called the ATLAS cavern, okay? And it is huge. This is like 10 stories tall. It's like some people describe it like building an underground like cathedral. I mean, it's bigger than this room for sure. And so here you can see sort of a diagram of how the assembly, it was like building, you know, a ship in a bottle. So we had to, you know, these are all the support structures because of course it's very heavy. And then the next things that we installed were these magnets, and everything comes down these 100 meters through some shafts, okay, that are basically connecting, and cranes. So I mean, these crane, the people that know how to operate these cranes are like magicians getting all this together. Okay, so then so once the magnets and all the support structures for the muons were installed, these are the calorimeters that go inside. And so we built, you know, we assembled them in these wedges. Remember that I mentioned that a lot of these wedges were what were built here in Illinois and then shipped over there. And then inside, this is the electromagnetic calorimeter. That was the hadronic calorimeter. And so we built these in pieces, okay? And then we would slide them in. It's like a jigsaw puzzle, you know, getting all the pieces one inside of the other. And then on the other side. So they're made, you know, it's sort of modular, but I mean, of course, each one of these is like several hundred tons. So not super easy to, not that portable, let's say. And then, so for the muons, the chambers that actually detect the muons that, you know, make it through the calorimeters, they were installed sort of one at a time and tested. So this was a lot of work, several years to get all this together. And then finally, so the calorimeters, we had to close them inside to be able to access all these muon chambers, and then we opened them up again, and then inside we put those tracking detectors. Remember that I mentioned that measure the trajectories of charged particles. And then on the very, very innermost layer, we have a tiny, tiny detectors that are pixels that are, you know, literally like your camera. So they can make very, very detailed measurements. So once we had, so this part of the cylinder we call the barrel, and once we had that set up, then these are the muon chambers. So that's that wheel that I showed you that didn't fit through the door. So then that one went in, and then this is the magnet, and of course, you know, this is a video, you're not allowed to stand over there, but you can see sort of the scale of the project. And so this is the magnet for the wheels, for the forward, you know, if the particles go in the forward direction. This is what bends those. And then here you can see, so the way that we built those big wheels are in these segments, these triangular segments that were lowered one at a time and then made into a wheel. And then we have lots of these wheels, and they perform different functions. So you've already seen examples of these, and then everything comes together, and then this is the beam pipe, so that's where the protons actually come in, and then they collide in the middle, and then of course we measure the decay products, and I believe that in a moment you're going to see, right, so this is showing you now the cutout, right, because otherwise you wouldn't be able to look at the different layers. Okay, so these are the calorimeters. And then if we peel those away, this is the electromagnetic calorimeter, right? So these are like the wedges that we just saw. And then this over here is the electromagnetic calorimeter. And then in here, then we have the tracking detectors that we just discussed. So these ones are made out of gas. These are gaseous materials. And then inside of those, you're going to see the silicon detectors. So now the scales really start getting, you know, very small. And we start, you know, these detectors, elements are, you know, centimeters away from the collision point, as opposed to the muon detectors that are just, you know, 25 or more meters away. Okay? And so you can see here for the scale. So now the scales are much smaller, right? If you were a person, you could practically walk through this, this calorimeter. And so the way that it would work is the protons would come along, right, on this 17-mile tunnel from the two sides, okay? And then, as I was saying, they come together exactly in the middle of our detector, and then they produce these sprays of particles that come out, and then the muons are the particles that make it all the way through, and we measure in this blue stuff. Okay, so so this video is of what was the plan for the installation. This one I promise you is very short, but here, so it's something fun that somebody did is they took a webcam and they took a picture, one per day, and this is what actually happened, how it was actually built. Okay, so you can see, all the huge amount of technicians and physicists and engineers that had to come together to just pull this off. I find this video kind of impressive. Actually, I heard that the first one that they lowered in the shaft, they had like a clearance of like a couple of centimeters on each side, and they couldn't quite get the angle. It was a real, I can't imagine, the person in charge of this must have been very tense to get that in there. Yeah, so then here you can see the big wheel. See, this is like years in like a very fast forward video. So it was really a major, that's the small wheel. Remember that I mentioned it came down in one piece. That was really impressive. And there you can see, boom, 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 done. Okay, so how do we use these detectors to measure things like the Higgs boson? So as I was mentioning before, we collide these protons together, and sometimes in these interactions, we can produce particles such as the Higgs. Now, the Higgs has a very short lifetime. It's 10 to the minus 22 seconds. So it basically decays instantly. And one interesting mode is when it can decay to Z bosons. And Z bosons, they also have, in turn, a very short lifetime. And they can in turn decay to leptons. So leptons, here we're talking about those nice muons or electrons that we measure in our detector. And so what we do is we basically use this formula. We take these two leptons and we apply the formula twice. Leptons are very light, so they have almost like no mass. And we can reconstruct each one of these Z bosons, and then we can combine them together to make a Higgs boson. And that is a bit more complicated formula, but basically, using these 4 leptons, we can identify what is the mass of the Higgs boson. And here you can see some, very nice displays of how a Higgs could decay into 4 muons. So here are the 4 muons that make it out into our detectors in blue. And then this is one of the events, real data events that we collected with our detectors that led us to discover the Higgs boson. Here you can see another event. I love it because, I worked on these forward detectors, and here we just had like all of our nice muons very, very nicely measured in the forward region over here. So we collected lots of these events. Here's another example. In this case, instead of going into muons, the Higgs went into electrons. So we have 4 of these with depositions in the calorimeters. And here you can see over time, so this took several years, we collected a bunch of data, and you can see, so in red, these are the processes that we already knew before we discovered the Higgs. And then this blue bump over here, and this is the mass of these 4 leptons, okay? This bump over here corresponds to the signal of a Higgs boson. So it took, a lot of years to build this detector. It took several more years to calibrate the detectors and take all the data, and eventually this was the signal that we saw, and that led to this very important discovery. Okay, so that is what I wanted to tell you about the LHC and ATLAS. So in a nutshell, we collide protons at very high energy, so they're going almost at the speed of light. We started in 2009. And the first run ended in 2012. That was when the Higgs discovery was announced. And now we've actually started running at higher energy, and we hope to discover new particles. For example, those dark matter, the dark matter particles, or anything else that might lie in store for us. I wanted to mention that we take lots of data. And of course, this was a major undertaking that involved, many countries. So over 85 countries were involved. We have more than 10,000 scientists working on this project. And what I wanted to do for the remaining portion is actually connect live to some scientists who are working at CERN right now, and they are at the operations center. So that's where we take the data, we make sure that our detectors are working properly, and so what I wanted is for them to tell you a little bit about themselves and what they are working on. And hold on a minute, let me unmute. Hello, can you hear us?
Hello, everyone.
Yeah. Okay, so
Can you hear us?
So please go ahead and please keep all your questions and don't be shy, okay? Please don't be shy and come over here and we can, from this microphone, I'm standing right here, you can ask them and ask me and anything at all that you might want to know, okay? Yes, please go ahead. Tell us where you are.
Well, hello everyone, first of all. Let me present first. I'm Roger, and I'm from Barcelona, but I'm working here at CERN. And
my name is Andrea. I'm also from Spain, from a very tiny place that you would not know. And I'm also working here studying a PhD with the University of Barcelona, actually. That's how I met Roger. And we're right here in the ATLAS control room, just on top of the biggest detector ever built.
Exactly. So this big detector that Verena was telling you is actually around 100 meters below us.
Yes.
So we are on top of each other. So this is where we have this detector, and behind us there is the ATLAS control room. So this is the place where they actually control this very big machine. So, I don't know. I mean, you already know many things that
Verena was telling you already how it works.
Let's explain maybe a couple of things as well, no? Just to introduce, and then we can go and see some of the screens that
they have
inside the room. So, well, as you know, I mean, the LHC is 27 kilometers. I don't have these in miles.
17
miles
more or less. 17 miles.
It's a bit weird because we are not used to these units. So this is basically a very big machine, built 100 meters below the ground. Then the reason actually this is very funny because, it's below the ground basically because like this it's well isolated, but also one of the reasons was that actually it was much cheaper to build this accelerator below the ground than to buy all the land that you needed to build the detector on top, let's say. So, but because Switzerland is one of the most expensive countries in the world, so I guess it was
land here is quite expensive.
So having said that, well, then we have this ATLAS detector that, you already know almost as much as we do about this, but it's basically, you have to think about that as if it was a camera, no? As if it was a camera just to take pictures, like the ones that you have at home, but basically taking photos of
all the particles that come out of the collision,
exactly.
and their direction and their energy and everything.
Exactly.
So the pictures are very big and very heavy.
Mm-hmm. So as big as more or less 100 megapixels. So each of the pictures, let's say that ATLAS takes, is around 100 megapixels. And the point is that it takes many pictures in a second. In particular, like 40 million. So you can see the amount of information that ATLAS creates. No, like a 100 megapixel picture, 40 million times per second, which is, the collisions actually, the protons actually cross at this rate. So that's why ATLAS is taking the picture.
Yeah.
But and actually, if we wanted to store all this information, we would be storing something like 1 petabyte per second. I don't know if you are familiar with these units, but well, you know the gigabyte, right? So 1,000 gigabytes is a terabyte, and 1,000 terabytes is a petabyte. So it's 1,000,000 gigas per second. Clearly, we cannot store all that. So
we have to decide what to store and what to not store. So what we have is something called a trigger system. So it kind of selects what events are going to be interesting for us. So can be leading us to new physics or interesting physics that we can study. So what it does is it reduces the rate of the interesting events, we say. So in the end, after passing the trigger, we store kind of 300 megabytes, right?
Yeah, something like 300 megabytes per second, which is not so much.
Yes.
And the good point is that also the trigger, that there is one of the guys that is behind us is also taking care of the trigger. So that's why we were explaining this.
Yeah, you will see it in a second.
So yeah, but the main idea is we take kind of pictures. They are not real pictures, right? We simply measure the different parts of the detector, but it's as if it was a picture.
Yeah.
So yeah, fun data. More or less, we can say that actually 300 megas per second doesn't sound like a lot, but this is working 24 hours all the days. So at the end, we stored in CDs all the information recorded since 2010, and then we put all these CDs one on top of the other. It will build a column of something like 20 kilometers, which I don't know in miles actually. Something like 13 miles or something like this. I don't know.
Yeah. Something.
20 kilometers. All right. So yeah. So having said that, maybe we can
take a look at the room. Maybe
you already saw that ATLAS is actually it's like somehow it's kind of an onion. No? I mean, it has like different layers,
yes.
right? And each of the layers has a different technology.
Different detector for different particles.
Exactly.
So here we have, in the control room, we have some people that take care of each of the layers, then some others that are taking care of more general stuff.
Exactly.
So yeah,
let me see if I can change the camera.
Yeah.
Now you're seeing the phone, right? Yes. Okay, so now...
So what time is it over there right now? It's
so
like 6:10.
Sorry?
Sorry, Vanessa?
No, I was just asking what time is it right now? It's like 6:10, right, p.m.?
Here?
Yeah, 6:10.
Yeah.
It's like 6:10 p.m. There are a few people taking care of our detectors.
Yeah.
Yeah, actually I don't think there are collisions now, so they're
working. I think that we started to run like a few times, some minutes ago.
Yeah.
So yeah, there is, as you can see, now it moved, and I don't know how. Exactly. So okay, so you see that this control room is basically divided into different desks, right?
Yeah.
So you see different tables.
There are many screens and many tables, but it's more or less divided depending on the system that they're taking care of.
Exactly.
So the main things are 6 tables with there's different desks and so on. And okay, this first one.
So we can start, for example, the one that you see at the end, but at this moment there is no one, which is bad. But maybe, I mean, okay. The people, by the way, the people that is here is doing shifts of 8 hours, and there are 3 shifts per day, so it's 24 hours working.
Yeah.
So as you can imagine, I mean, people that is here and needs to go to the toilet, for example, no? Needs to go to grab something for it for a moment, right? So maybe that's the case.
Probably the case.
We cannot blame the guy.
Also, the people that are now in the control room don't just work here. These are shifts that everybody takes in the collaboration, because this is a collaboration. So we come here, and even Roger and me, we also do this. Everybody that wants to analyze data and use ATLAS maybe has to take shifts. So every year, each institution that contributes to ATLAS has to do some number of shifts. So that's how we manage to always have people here and not having specialized people. It's just the physicists and the engineers that work in ATLAS normally.
Exactly.
So by the way, guys, this gentleman in the front, he's the Muon expert. He's one of my colleagues.
Okay.
So that is someone.
Yes.
That's good to know. So as you see, I'm coming back to what we were saying before. There are different tables. So the one that you see at the end is the one that actually precisely taking care of the muons. So this table is basically checking that the muon spectrometer that Verena was mentioning at some point, that everything is okay, that it's taking data correctly, let's say, that everything works. Exactly.
Then if something doesn't work, there is always someone also on shift on call. So they're at their house or doing their lives normally, but you can call them anytime in the 40, I don't know how long they are, like 2 weeks or something, no?
When I said it was 2 weeks.
Yeah. So in these 2 weeks, they can call you at any time for fixing some problem that you have in the control room.
Exactly. Normally, I mean, sometimes at night.
Yes.
But, you know, Murphy is slow.
Yes.
So yeah. So then, for example, if we move to another table, unfortunately, I cannot zoom the camera, but the table that is in front of the muon one, this is the one that is taking care of the trigger. So this table is exactly, if you can point.
This table over here.
Exactly. So these guys basically are taking care that, I mean, the rates of the triggers, are fine, and that we are. In general, like recording data, I mean, that everything is fine. Then there is a table, I mean, coming to us, let's say the table in the middle, but in the front. This one is basically, I mean, there is the guy that
you can see the hand
controls the software used for this, which is called the run control. And also there is a person in charge of the security, let's say, or in charge of all the accesses and etc. And here maybe we can mention that.
He has a set of keys in the box there on the table.
I think you need to turn a little bit. I think you need to turn the camera a little bit.
Let me see. Maybe
we cannot see the keys.
Okay, let me.
Wait a second, because what happens? I'm trying. Yeah, maybe you can explain for the moment.
Yeah. Okay. So what I was saying is, in the front middle desk, there is a table, a box with some set of keys. One of which you need when you want to go underground to the detector. So when we're taking data, all the keys have to be when the beam is in. All the keys have to be in this box. So this way we make sure that there's no one downstairs while we're starting the beam, because that would be very, very dangerous. So yeah, if you have the key, there cannot be a beam going on. So this is how we make sure that everything is okay. We also, ATLAS, here we take out, in CERN in general, we take care a lot of security.
Here we go.
Roger managed to move the camera, that's great.
Yes.
We also care about security a lot for going inside the detector, underground. You need not only this key, you also need our eye scan and everything. It will really take care of it. So yeah, here you can see this desk we're talking about, right?
Exactly.
Yeah, so this is the main person taking the data in ATLAS, like actually running everything, the whole 100 million channels, that gentleman over there.
Yeah.
Great. Okay. So the next, the desk behind that one is where the run coordinator is, and also a shift leader, right?
Yes.
That's
So we moved again the camera.
Yes. The problem is that
sorry about
ran
that.
out of battery.
We have a remote control, but it ran out of battery while we were watching your presentation. So now we have to go inside the room to change the cameras and everything, but it's okay. So yeah, I was saying that desk there takes care of, it's the run coordination desk and also the shift leader, so it's like the ones that coordinate everything, as the name says, I guess. And then as soon as we manage to turn the camera, I will tell you a bit about the others.
This is exactly, so the one that you see below is actually the one that coordinates. The tables that you see in front of you is what you were saying about the security, no?
This is the security.
And then we are reaching, let's say, the other part.
These are the event displays showing the data live that we're collecting in our collisions. Yeah.
Yes, exactly. So maybe, so I guess.
So these are like those displays that I was showing you, those images, so we can see what's actually happening downstairs in real time. And actually, we put that on the web. If you look for live ATLAS collisions, you can see what's happening.
It's always in streaming.
Yeah, exactly. So you see, for example, in the screens at the end, more or less, you have live events. So this is real data that we are taking now. Well, they are random events that are then projected here. So you can see this is, let's say, once you've collided the particles, let's say the bunch of products, the bunch of other particles that appear, and that's what they are. That's what is shown in this screen. Then, actually, in green, you can see the ATLAS detector, and this what basically tells us is that all the subsystems are working correctly, let's say, which is good, no?
If it were red, we would know there would be problems. That's how we...
Sorry?
No, I was just saying that green means everything is on, and if there are red bits, we know that those are parts of the detector that are not working.
Exactly.
Green is good.
Yeah, exactly. So this is regarding the control room. So you see, let's say the message is that there is a lot of people taking care of that, and that there is even more people behind the scenes taking care of the people that is in the control room. Let's say, because when something doesn't work, then these guys call the expert, and then is the expert the one that actually solves the problems.
So shall we see if there are questions from our audience? Please, please, do you have any curiosities? Please come down here, and if you don't mind speaking to this microphone so that they can hear you in turn. We have a few people, so please don't be shy. This is your opportunity to ask. Yes.
Hola. If dark matter is a particle, has the theory been worked out what the maximum energy has to be so that it can be discovered, or I should say that your detector has to ramp up to detect it if it's some maximum amount of energy? I guess I'm asking, do you know what the maximum energy of a dark matter particle cannot exceed?
Did you guys hear the question?
The maximum energy of the
that a dark matter particle could have.
That you can see.
Yeah, well...
Oh, that we could see. What is the maximum energy of a dark matter particle that we could see?
Or...
That we could see. Well, we're colliding protons at 13 TeV, so...
Yeah, but the point... Sorry.
Yeah.
Technical problem. But the point, concerning, what we are talking about is dark matter. Actually, dark matter is called dark matter because it actually, we cannot, it doesn't interact, for example, with light. That's why we call it dark. And in our case, if it existed, it wouldn't interact with our detector.
Yeah.
So we would be able to kind of indirectly see it by, let's say, we know that when there is a collision, the energy is conserved. So we know the energy at the beginning, we can measure the energy at the end. If there is something that's missing, that would be, let's say, a dark matter particle, if you want.
Yeah.
The point is that there are other particles that don't interact with our detector either. For example, those are the neutrinos that Verena mentioned at the beginning. And then, one of the work, or what we need to see is to see the cases where we have a neutrino, control very well these kind of processes, and then if we see any excess, let's say on top of what we expect from neutrinos, then these could be dark matter, for example.
Yeah.
And what would be,
But
so the
we don't
energy
see directly the dark matter.
Yeah.
in principle, we could go up to TeVs, right? Sorry, in principle, we could go up to TeVs for particles. That's what we can measure in our detector, right? As much energy as we put in, basically, pretty much.
Exactly.
Okay, next question.
How do we actually know that quarks can't be split into smaller fundamental particles?
I'm not sure. Did you hear?
No, I didn't hear.
Yeah, can you repeat
So the question was,
Uh,
sorry, can you come over here because yeah.
How do we know that quarks cannot be split into smaller fundamental particles?
That quarks cannot be
Split into more fundamental particles is what he wants to know.
Well, we actually don't know.
Yeah, it could be. That's why we are still investigating.
That's one of the things that we would like to see.
We haven't ever seen a quark dividing into something smaller, but it could happen, so that's why we're still working here.
We're trying to see smaller scales. Exactly. That's a great question.
That's a bit the objective. I mean,
Yeah.
we try always to go like to smaller and smaller and smaller and smaller scales.
Yeah.
For the moment, I mean, we haven't found anything smaller, if you want. But of course, I mean, at the beginning, like 100 years ago, I mean, they were thinking the same about the proton, maybe.
Or the atom even.
Or the atom, right?
Yeah.
And then, I mean, we went like deeper and deeper, and we found that this was actually
Yeah, as
something
before.
else. So yeah, who knows? Maybe we find that there is something smaller.
Maybe in the future you can join us. Try to find.
Maybe you can discover it.
You're welcome to come.
Thank you. Please go ahead. If you can speak over.
I've been interested in the philosophy of science, and the CMS detector, anyway, did its experiments blinded. And I'm curious as to how they managed to get 1,000 people to agree to this rather onerous way of doing science. And if so, how did they actually manage to, coordinate that so that people didn't know what was the data that was being taken in the, I guess it was the Higgs experiments.
Yeah. Well, this is a common technique to blind the data before. So what we do is first make sure that we can control all the backgrounds so that we know how our simulations work, and then after that you can look at the data so that you.
Exactly. So the idea behind blinding is not to be biased by what you see there, right? Because you can imagine, for example, that's what Andrea was saying. If you have a process, I mean, if you have a simulation and the simulation is wrong, and you try to blindly, let's say, then I mean, you look and, for example, imagine that you have the Higgs there, but since your simulation about other processes that might also have the same final state is similar, it's wrong, sorry. I mean, what it happens is that, for example, you might be missing your signal, which in this case is the Higgs, or you can even be creating a signal because your background estimation or your simulations are wrong.
Yeah, and it's also a matter of how you see it, because it could happen that you don't think that the new particle is going to be there. So if you see an excess, you say, oh, I'm probably doing something wrong. Or the opposite, like you want to see an excess because you want to discover something and then you see it where it's not. So you want to first control the background very well and then look at the data and be sure that what you're seeing is fine.
Exactly. So it's basically to avoid the bias.
Yeah.
Does ATLAS do that?
Then of
Yes,
course,
absolutely.
it's difficult to coordinate that among so many people. CMS has a lot of people, ATLAS has a lot of people.
Yes.
Yeah, it's very, when everyone wants to look at the data, right?
Yes. So ATLAS also blinds for the Higgs searches, for example. We had not seen that peak until a few days before it was presented to everybody.
Exactly. Yeah.
So we also, because we want to avoid these kind of things. Yes, we have another question.
But the nice thing about that, for example, was that ATLAS blinded. So only those doing the analysis that they knew everything. And also CMS did the same, but I mean they were independent one from the other. No, it's different collisions one from the other, and still I mean we found the Higgs in the sense that this gives security that what we have found is not fake. It's well measured, right? Because two independent sources, let's say, have found the same thing. And also like doing all this prevention, let's say, to avoid biasing, which is blinding and all these things. So this actually gives us a lot of security. And in my opinion, this is very nice. No?
Yes. I think it's more or less the purpose of having two very similar detectors is to check that if one finds something, the other should also find it. Because in the end, they have similar data in principle. So it's a way of being sure that what you discovered is not something crazy.
Okay, thank you. We have another question, please.
Thank you. So this facility is such a great job and making me willing to participate in maybe in the future. And suppose in the future we are going to build an even stronger accelerator. So like engineering aspect, how could we improve the energy, maximum energy we can give to those photons in the collision? Like, is it about the electromagnetic coils or about like what kind of aspect?
Yeah, what are sort of some of the technical aspects? So,
For building a bigger detector,
he's asking about future colliders. So we are discussing.
There is a project.
Well, we still actually don't know which is the
still don't.
collider that will come after that one. There are many projects
Yeah, for
that
now
are competing.
we have an HC which has 13 TeV of maximum energy. Then there is an upgrade for it so that we will have the same energy but more luminosity, so there will be more collisions per second. And after this, we don't know. There is a project of building a linear accelerator that is electron positron, which I think is like 50 kilometers long. But I'm not sure.
And one of the projects that was also here was the so-called super LHC, that would be like a similar, let's say, accelerator like the one that we have here, but that instead of having 27 kilometers, this one would have 100 kilometers.
Yeah.
And actually the LHC, the one that we have now, would be used as a pre-accelerator, to like accelerate the particles and then would go into the super LHC. But of course, I mean, this also depends on what we find here, right? I mean, if we discover some new particles, depending on how these new particles are, then you might want to build a specific accelerator with specific detectors to actually
go after those
study this new particle more. No? So these can actually be used to decide which kind of detector we use.
Yes. I also think that there was a similar project like this for 100 circular accelerator in China, that if it's not approved already, it was close to. So it's more, I mean, I don't know what the stage of the one here is, but this one was pretty advanced. So could be.
So in consideration
about the technology, this is also evolving with in the current. For example, now actually we were very lucky because these guys here are going to, well, not these guys, but I mean, there will be people here until Monday, and then Monday we stop for 4 months because this is basically used to, let's say, fix the things that, for example, some parts of the detector stopped working, for example, or not, because I mean, while there are collisions, no one can enter the tower, so then you need to stop from time to time, and then go down, and then fix the things. And then from time to time, also in this long shutdown, sometimes you also upgrade some parts of the technology. So this is, the detector is continuously evolving, let's say.
Okay.
Yeah.
So
both
like,
the detector and the accelerator.
And the accelerator.
Are changing.
for your now current like data capability, the energy is already enough, right? We got a lot of data and we do not need like even higher energy for that case. Is it true?
Well, it depends on where the new physics is, right? So we don't know what energy will, these new particles have. So we, at the moment, are collecting a lot of data, and we're going to study this energy range. And we hopefully, we will find something new there. If not, future accelerators we can build can go to higher energies, and then we can continue to look for new things.
It's
so
not
that's
the higher the byte. It's a range.
yes.
Okay.
So and what's really nice about these proton accelerators is that because protons are composite particles, actually the particles that are interacting are the quarks and gluons, and they have a range of energies. Because they're inside of the protons, so we can actually study collisions of lots of different energy ranges, up to a maximum of the total proton energy. Sorry, we have one more question, and if you don't mind coming down, I'm sorry.
No, it's so simple. What's the highest speed that they can get the protons to go to?
Sorry, what is the highest?
What's the highest velocity they can get the protons to go to?
Oh, so I have that in my slide. It's like 99.999999.3% the speed of light.
Oh, okay.
So it's
the speed of the particle, sorry, I didn't.
yeah, it's almost at the speed of light. We can't quite get it there, but
How can you get more energy?
When they speed, when we are speeding in the galaxy, they do more or less 11,000 turns in the accelerator per second. Just for you to have an idea of how fast they are. So it's 27 kilometers, they do 11,000 turns a second. Revolutions per second, so fast.
One thing I wanted to say is that, so one part is to give energy to the protons. And so as they go around, they turn around, we give them more and more energy. But it turns out that one of the biggest limitation is actually from the magnets. Because we need to keep the protons in a circle. And they are so energetic, they don't want to go in a circle, they just want to fly off. And so that is the whole challenge, is to build these very powerful magnets that can keep these protons, just keep them in the circle. And so that is sort of the limitation. And as I showed you in my slides, so it depends on the magnetic field. And the other way that you can do it is by building a bigger tunnel. But of course that's civil engineering and that's also expensive. So this is what we're trying to do.
The same as when you take the car, for example, and you go to the motorway. No? I mean, sometimes there are some turns in the road. No? If you do them like very slowly, you see that you go straight. No? But if you go super fast and you turn a bit your car, no? I mean, you go to the, you feel really the force, no? the centrifugal force. So that's more or less the same idea. I mean, protons are going so fast that even though the accelerator is 27 kilometers, they actually feel a lot the acceleration, no? the force that you have to apply to them to turn, to make them turn. That's why, Verena was saying, I mean, we want to build the biggest, a bigger accelerator so that these protons don't feel so that let's say the radius is larger, so you don't feel so much the force, and they can go to higher speeds.
Okay, we have our last question. Please come. Sorry, this is so that they can hear you.
Yeah, just very simple. Why do you come to CERN? So we understand that you help with the control room, but you need to be at CERN in order to analyze the data, or are you working on new designs for collisions, or detectors, or triggers, or just working with international teams by being there?
Well, there are some people that need to be here, like the designers and the engineers and everything really need to be here to test it and try it and see if everything works. But we are physicists, we really don't need to be here. We can analyze data from wherever. Actually, we have a network of computers all over the world where all the data is stored.
Actually, the World Wide Web was invented here precisely because of this, so that the data could be distributed among physicists.
Yeah, it's an easy way of sharing.
Exactly. So no, I mean, being a physicist, you don't need to be here, but that's good. It's also
it's very helpful to be here.
Exactly.
We have meetings every week, and usually every week several times. So it's easier because this is a collaboration. So we talk with a lot of people, we work with different groups and so on, and it's much easier to interact. You are here and you can see them and you can have a coffee with them even.
Most of the world experts about something are here. That means that if you have a problem and you want to ask them, it's much easier to go to their office and knock on their door and ask them directly than to send them an email that then you get the answer. I mean, like they are fast, they get the answer the same day, no? But if not, you can wait for days, for the answer, right? So it's much more convenient to be here. It's not mandatory, of course, in general.
And actually, many of the people don't come here because it's also for the institutes, it's more expensive to send them and so on. But yeah, it's helpful.
Yeah.
So the last thing I wanted to say is that if you ever find yourself in Geneva, Switzerland, you are very welcome to visit CERN. CERN gets hundreds of thousands of visitors every year. And also another great place to learn about all this physics and see all the detectors is Fermilab, which is a much shorter trip. And visitors are very welcome there too. As you can see, we physicists love to talk about our work and our experiments, and we like to show off our detectors. So you are all very welcome. Thank you for listening. We have a last message from CERN.
Yeah, no, we wanted to show you something,
Yeah.
just to show you that
Yeah, we didn't finish with the tables in the control room, but
exactly,
there's something very
that
nice.
we wanted to show you, and
yes.
let's
Yeah,
let's see.
he's already an expert in this ATLAS virtual visits, and this is something that he likes to say every time, and it's a very funny fact. So he will change the camera so that you can see it, and we can tell you what it's about. So the thing is that, okay, maybe, yeah. Okay, so these are the two last tables that we didn't see. The one in the back is for the calorimeters. The one in the front. So here you see in the screens you can see the detector and how everything is green and so on. But you can see there on the table that there is a little duck. Maybe you wonder why that's there.
I don't know, I wondered that the first time I came. Should be in a shower, not in a control room.
So actually this is the desk of the guy who takes care of the data acquisition, which we shorten as DAC. So yeah, just as a joke, the DAC is always in this table.
Yeah. So we make jokes from time to time.
Yeah.
Okay, thank you very much. Thank you guys for connecting.